Hello, in this video, I will talk about identification requirements and estimation methods for confirmatory factor analysis. So to estimate a confirmatory factor analysis, it's helpful to think about an example. So let's say we are trying to measure satisfaction. So we have a confirmatory factor analysis model like this one. Here we have job satisfaction and three indicators of job satisfaction, and each of them has a measurement error. Okay. Now, to estimate this model, we first need to place some constraints in it. The parameters here to be estimated are the variance of job satisfaction, so the variance of the latent factor, three factor loadings, lambda 1, lambda 2, lambda 3, and three measurement error variances, like so var E1, var E2, and var E3, okay? Now, these are 7 parameters to be estimated, but we can't estimate all of them, and I will explain momentarily why not. So when you are trying to measure a latent variable, there is a problem of origin and scale indeterminacy. Well, this happens because a latent variable doesn't have a natural scale of measurement, so there is no true 0 point. Like, what's zero's job satisfaction? That's not defined. Also, it doesn't have a scale. In other words, what does it mean to have a 1 point increase in job satisfaction? So to be able to estimate confirmatory factor analysis, you need to set the scale for the latent variable. There are 2 ways of doing it. So in Amos, the default is to set the mean of the latent variable to 0, and to set the first factor loading to 1 to set the scale. So what does that mean? So you have here job satisfaction again with 3 indicators. So we will set the mean of job satisfaction to 0. That means that if someone is found to have 0 job satisfaction, that can be interpreted that job satisfaction is of that person is equal to the mean. And then also, the implication is that, half of your sample will have negative job satisfaction and half of your sample will be positive job satisfaction. Having a negative job satisfaction just means that someone is below the mean. And then to set the scale, we set 1 factor loading to 1, which means we don't estimate that factor loading, it's fixed. Therefore, instead of having 7 parameters to be estimated, we have only 6 because that factor loading is no longer estimated. The second method is, instead of setting the factor loading to 1, we set the variance of the latent variable to 1. You say the var of job satisfaction equals 1, and then we freely estimate this factor loading here. This standardizes the factor. Therefore, someone that has a job satisfaction of +1 is 1 standard deviation above the mean of job satisfaction, and someone has job satisfaction of -1 is 1 standard deviation below the mean of job satisfaction. So these 2 methods are equivalent statistically, like you get exactly the same model fit, and exactly the same standardized results, regardless of whether you set a factor loading to 1 or the variance of the related variable to 1. So it doesn't really matter which approach you pick. But you have to pick one or else the model will not run. Now, identification requirement. The basic identification requirement of all structured equation models is that degrees of freedom is non-negative. Now, let's look at our job satisfaction model here. So I have job satisfaction here with 3 indicators. And let's say that we decide to set the mean of the factor loading, the mean of the factor to 0 and the first factor loading to 1. This leaves 6 parameters to be estimated. Factor loading 2, factor loading 3, and 3 error variances. And factor variance. That is 6 parameters to be estimated. Now, how do we calculate the degrees of freedom here? We have to count how many elements there are in the covariance matrix. So for a covariance matrix between 3 variables, we have 3 variances and 3 covariances. Therefore, we have 6 elements in the covariance matrix. The degrees of freedom then will be df equals 6 minus 6, because the 6 parameters are estimating zeros. So this model is just identified. There is 0 degrees of freedom. It can be estimated, but you cannot evaluate model fit because a just identified model is saturated. Now, there is a quick formula to calculate the number of elements of the covariance matrix. The formula is the number of variables times the number of variables plus 1 divided by 2. In this case here would be 3 variables times 4 divided by 2 equals 6. Now, what's the minimum requirement there to have at least 0 degrees of freedom in CFA? Well, if you have only one factor, you need at least 3 indicators. That will give you a degrees of freedom 0, but you can estimate the model. However, if you have more than 2 factors, you need at least 2 indicators per factor. So in a situation like this, let's say we have job satisfaction and organizational commitment as 2 factors. Each of them had 2 indicators. This model would be identified. Let's count how many parameters we're estimating. So to set scale of job satisfaction organizational commitment, you need to fix a factor loading in each of them to 1 or set both factor variances to 1. So I'll set the factor load. So this factor load is 1, this factor load is 1. We are freely estimating these 2. We are estimating 2 factor loads, we're estimating 4 error variances. So that's 6 parameters. And then we are estimating 2 factor variances, that's 8 parameters. And then we are estimating, typically we would also estimate the covariance between job satisfaction and organizational commitment. So that gives us 9 parameters that we are estimating. How many pieces of information we have? We have 4 variables here times 5 divided by 2. The covariance matrix has 10 elements. So this model here will have a degree of freedom equals 1. Okay, so if you have more than two factors, but if you have items that load in more than one factor, it gets more complicated. So let's say you have a situation like this. You have job satisfaction and organizational commitment, but in your scale, 6 items here, there is one item that measures both job satisfaction and organizational commitment. It's possible. Items can measure more than one factor. Is this model identified? Well, you have to check the identification rule here. So you need to have at least S minus 1 factor load is set to 0 for each of the S factors. So there are 2 factors here. Therefore, I need to have S minus 1 is 1, S is 2 minus 1 is 1. Therefore, I need to have at least 1 factor 0 for each of the factors. For this model here, this means that there must be at least one indicator that's unique to that factor. In other words, here there are 2 indicators that only measure job satisfaction, and 3 indicators that only measure organizational commitment. Therefore, it meets this requirement. I could even have more arrows. I could have this arrow here, and I could have this arrow here. In this case, as long as I have over here one indicator that only measures job satisfaction and one indicator that only measures organizational commitment, it would still be identified. Now, it's usually we assume local independence. Therefore, we assume this. Once, if I have a model here, let's go back to job satisfaction and organizational commitment. And we assume then that once you account, you have 4 items here, 4 indicators. And once you account for job satisfaction and organizational commitment, whatever is left of variabilities indicators is the residual variability is random. And that means local independence. Like local independence means that once you account for job satisfaction and organizational commitment, the residuals of these indicators are uncorrelated. So there shouldn't be a double-headed arrow here. If there was, then you will be violating local independence. Another couple assumption is that the residuals are uncorrelated with the latent variable, so no double-headed error between the latent variable and the residual. And the residuals for different factors are also uncorrelated. So this means that, if you have an indicator, once you account for the latent variable it's supposed to be measuring, whatever it's left is random error, right? So these can be simplified I'll put this in an equation for you. This means the response, so the response to a job satisfaction question equals to the factor plus error. And that error is random error. Now, how do you estimate a structural equation model? There are several estimators maximum likelihood, weighted least squares, unweighted least squares, diagonally weighted least squares. But the most common by far is maximum likelihood. So the maximum likelihood estimation, it minimizes this discrepancy function here. So this discrepancy function is a way to quantify the difference between the implied covariance matrix. Remember, the implied covariance matrix represents what the covariance matrix should be if your model is correct. The observed covariance matrix, which is the data, right? And if the implied covariance matrix matches exactly the observed covariance matrix, you have exact fit. Therefore, this discrepancy function here is going to be 0, right? So try to fit the model is to try to minimize, find the parameter values that minimize the discrepancy function. This is typically done iteratively with optimization method. And sometimes, however, sometimes maximum likelihood estimation gives you estimates. Okay, what are impossible estimates, or also known as improper or inadmissible estimates in structural equation modeling, are either when there is a negative variance or a correlation that's with absolute value larger than 1. So it's a correlation that's either smaller than -1 or greater than +1. Those are impossible. But this could happen. In that case, you have to do something about it. What are possible causes of inadmissible solutions? You could have a model that's just very misspecified, and then the solution will be trying to specify it. Empirical non-identification is where some of your correlations that are expected to be non-zero because of the implied covariance matrix, they're actually 0 in the sample. So it's like you're missing information there. Very small variances, like your data has numbers like 0.001, 0.002, and the variance of these numbers is also very small. Well, the solution for that is just scale your data. If you multiply your data by 10, the variance will be multiplied by 10 squared. And that will solve this problem. Multicollinearity, which is when variables are very strongly related. So if you have two variables that are their correlation is 0.99, they're redundant. So they're not providing two pieces of information, they're providing one piece of information. So you can have an improper solution. Poor starting values is something that's not much of an issue anymore because modern structural equation modeling software has good starting values usually. Okay. So this is a list of solutions. If the problem is model misspecification, revise the model. If it's empirical non-identification, so you have a correlation in your data that's very small, you may remove a path that depends on that correlation, or even remove a whole variable from your model. If the cause is very small variances, set the variance to 0 in the model or rescale your data. You may also have estimation problems if your variances are very large. So that happens, for example, if you have income in your model. Income per year typically has a very large variance. What I do typically is divide income by 1,000 or even by 10,000, and that gives a variable that has a smaller, but not too small variance. Poor starting values usually doesn't happen. And multicollinearity, usually you remove a redundant variable. So that's how you do identification and estimation in confirmatory factor analysis.